And thanks again for organizing the summer school and inviting me to come give a talk. So today I'm going to talk about safe reinforcement learning and safe reinforcement learning algorithms. But I guess I'll start with just an overview of what I'm going to talk about in this talk so you know what to expect. I'm going to start off by just giving some background, make sure we're on the same page about notation. And I'll give some motivation for why it is that we need safe reinforcement learning algorithms. I'll then talk about what I mean when I say a safe reinforcement learning algorithm, and also what some other people mean. So I'll give you a very quick overview of some other definitions of safety within reinforcement learning. I'll then talk about 3 different steps towards developing a safe RL algorithm. There are 3 subcomponents, 3 sub-problems that we can actually study pretty much independently. And that's off-policy evaluation, high-confidence off-policy evaluation, and then actually constructing the safe algorithm. And then finally, I'll talk about some experimental results to show that this isn't just theoretical talking, this actually works. And then I'll conclude and talk about some possible future directions and also give references all kind of there at the end. Okay, so first, background. I mean, we've seen this repeatedly over and over, but we're in the RL setting. So we have an agent interacting with an environment. That agent is observing the current state of the environment, choosing an action. That action changes the state of the environment, and the agent gets that reward signal. Just the standard MDP setting. And our goal is to find an optimal policy. That's the optimal mapping from states to actions. And in this talk, we're going to generally focus on episodic MDPs. So this cycle repeats for some number of steps, and then it stops, which you can view as we enter some terminal absorbing state. We reach a state from which we never leave, and the rewards are all 0. So it's an episodic setting. Also, we're going to deal with the case where this mapping, this policy, can be deterministic or stochastic. But there's going to be some cases where we require stochastic policies. So when I say stochastic policy, I just mean that the policy produces a distribution over actions. It doesn't deterministically select an action. Okay, so what notation am I going to use for this talk? I'm going to use pi for policy. So pi of a given s is the probability of action A in state S. I'm going to use h for history, and I'm going to say history instead of trajectory. And that's just to simplify some notation so that we don't use t for time and trajectory. So h, a history, is just an observed sequence of states, actions, and rewards. And I said we're going to focus on the episodic setting where we terminate after some amount of time. And so L is going to be the horizon of this problem, the number of decisions that we have to make before this process terminates. Okay, so h is a history or a trajectory or an episode. The historical data D, so I'm going to talk a bunch about this historical data later. It's just going to be a set of observed trajectories or histories. It's data that we've collected from running some existing policy. And this historical data was generated by running a policy that I'll call the behavior policy, pi b. And our objective, as discussed before, is expected return. So we want to find the policy that maximizes the total amount of reward that we get. And I'm going to use the symbol J to note the performance of a policy pi, which is just that expected sum of rewards given that we're using that policy. So pretty standard notation. It's pretty similar to what Rich was using in his talk. Okay, so I've set this up using MDP notation. And for the rest of the talk, I'm pretty much going to stick to MDP notation. But it's worth noting that when we talk about safety issues, it's important that we're robust to things like partial observability. The real world isn't some very simple MDP where we observe the full state of the environment. We have sensors that make observations, and those sensors are noisy and perhaps unreliable. And so really we should model the world as a POMDP, a partially observable MDP. So our agent isn't directly observing the full state of the world. It's making some observation about the world via some sensors. And these observations can be noisy, they can be incorrect. And this is the POMDP setting. Everything that I'm going to talk about carries over to this POMDP setting, even though I'm going to be talking about the MDP setting mainly. So it's just an important thing to keep in mind that this will be robust to partial observability. Okay, so let's talk about some potential applications where we might care about ensuring different forms of safety. So the first one is digital marketing. And so here I visited Adobe's website, and they showed me an ad for Creative Cloud, and actually a second one for Photoshop. And these ads aren't deterministically chosen. They're not the same for everyone. They're not completely random. They're targeted specifically at you, the visitor to the web page. And so this process of targeting advertisements can be viewed as a sequential decision problem. So here, let's ignore the state for a second. The observation is the vector that captures everything that we know about you, the visitor to the web page, when you come to our web page. The action is then a decision about which ad or type of ad are we going to show to you. And the reward is +1 if you click on the advertisement and 0 if you don't click on the advertisement. And this is actually a sequential problem. Often this is treated as a bandit problem, but it's really sequential. What's the sequential nature? Well, our observation at one step depends on the action that we chose at the previous step. We showed you an advertisement, which you either clicked on or didn't click on, and that changes our beliefs about what you might be interested in or might not be interested in. And so the observation vector at one step is closely dependent on the action that we chose at the previous step. So this is digital marketing as a sequential decision problem. Why do we care about safety here? Well, if we deploy a reinforcement learning algorithm to this problem, and it does very poorly, it starts deploying advertisements that actually there's a much lower chance that you click on it, it can result in significantly decreased revenues. And so for companies, like for example, Adobe has a product called Test and Target, which serves up advertisements for other companies. If they use reinforcement learning in a product and it ends up producing policies that are worse, they could end up losing customers. So it could be very expensive to a company if an RL algorithm for this task doesn't perform properly. Okay, what's another example? Another example is intelligent tutoring systems. So I'm currently a postdoc at CMU working with Emma Brunskill, and so I'm biased towards these applications. I like them a lot because Emma's doing these intelligent tutoring system applications. The idea here is that we have a student that's learning about a topic. This is a game, so it's not a course in this case, it's a game, but it's the same concept. And here the student is learning about fractions. So the student's controlling the frog, and they have to click 2/6, I think it says, 2/6 of the way up the chain, and that's where the weak point on the chain is, and if they click it correctly, then the frog breaks through and they can continue. And they solve a sequence of these problems. Where's the RL task here? The task is that if we give a student a problem that's too hard, then they can get frustrated and stop playing. If we only give them problems that are too easy, then they're not going to learn anything. So the task here is to choose what type of problem to give next, how to order topics, how difficult of a problem to give next, to maximize a student's understanding at the end of a course or after playing one of these games. So what would our sequence, what would our setting here, what would our setting be where this is a sequential decision problem? So our observation here is everything that we know about the student, what we think they understand right now. Our action is then a decision about what type of problem to give them next or how difficult of a problem to give them next. And in this case, for this game called Tree Frog, the rewards were actually 0 all the way through. And then at the end, the student took a test on the topic on fractions, and the student's score on that exam was the only reward for this entire history, this entire episode. And so what we're trying to do is maximize the student's score on this post-test. So find the way of serving up problems to a student to maximize their understanding of this topic after the course. Why does safety matter here? Well, if we deploy a policy that's worse, then we can discourage a person from learning more about this topic, make them think I'm not good at math or I don't like math. And so it's important that when we deploy learning algorithms here, that they work properly. Another one is functional electrical stimulation. So this is work that I did at Case Western Reserve University during my master's thesis. And the idea is that when someone's paralyzed, their muscles and nervous system are still intact below the break often. And so you can directly stimulate the muscles in a person's arm, a paralyzed person's arm, in order to move their arm for them. And so the question was, can we control a paralyzed person's arm to move it from some initial position to some target position? And researchers at Case Western Reserve University, working with researchers at the Cleveland Clinic, did this. And they used a proportional derivative controller, a standard control technique. And it worked, but only reasonably well. The problem was that the individual person's arm didn't exactly match their model of an ideal arm. And so they asked, can we create a controller that adapts to this individual person's arm to make the control movements more smooth? Or in this case, so that they would land at the correct target position. And this can be modeled as an MDP. I'm guessing you can all see exactly why. And again, safety is an issue. If you're trying to drink, you don't want this person pouring things over themselves. Or even worse, in this exact setup, if you give the wrong stimulations in the wrong states, you can dislocate the person's shoulder. And this is something that we really want to make sure we don't do. We don't want to deploy a learning algorithm that does this unsafe behavior. And the last one, which is really, I think, the best motivation for why we need these safe algorithms, is type 1 diabetes treatment. So first, what is diabetes and what is the RL problem here? So when you eat a meal, the carbohydrates in the meal cause your blood sugar to increase. Your body then releases insulin, which promotes the absorption of the sugar from your blood into various cells of your body. So throughout the day, your blood sugar makes a plot that looks like this. This is minutes since midnight, so this is 1 day. And this vertical axis is your current blood sugar. And this is many simulated days using a simulator. This is your blood sugar spiking because of breakfast, lunch, and dinner. And for this particular person, green is ideal blood sugar levels and black is the limit of healthy levels. Okay, so what is the problem in type 1 diabetes? Someone with type 1 diabetes, their body doesn't release enough insulin. And this means that their blood sugar levels tend to be too high, which is a condition called hyperglycemia. Hyper for high. So hyperglycemia is when their blood sugar tends to be too high because there's not enough insulin promoting absorption and pulling the blood sugar down. Extended instances of hyperglycemia can lead to ketoacidosis, and I think it's the leading cause of non-traumatic adult amputations. So extended hyperglycemia is a problem. So to fix this, what someone can do is inject additional insulin into their blood, either directly or through an insulin pump. And if they don't inject enough, they'll still suffer from hyperglycemia, high blood sugar. And if they inject too much, if they put too much insulin into their blood and promote too much the absorption of sugar from the blood into the cells, it results in hypoglycemia. And it's really easy to mix these up. It's just one letter different, but hyper is too high, hypo is too low. So hypoglycemia, low blood sugar, is significantly worse than hyperglycemia. Severe instances of hypoglycemia can triple the 5-year mortality rate for a person with type 1 diabetes, and it can lead to loss of consciousness, which is devastating if you're driving, for example. So this is a control task. It's a task where we'd like to decide how much insulin should someone inject prior to a meal in order to keep their blood sugar levels near optimal, without driving it too low, and to try to keep it from being too high. Okay, so it's a control problem, so we can try to address it as a control problem. And actually, what is done now is in an insulin pump, there's an equation that decides roughly how much insulin someone should inject. And this is kind of a simple form of one of those equations. And it's a controller, if you're familiar with PD controllers. This is the proportional term, this is the derivative term. So what is this? Let's go through it. The size of the injection is the person's current blood glucose, the current amount of sugar in their blood, measured from a blood sample, minus their target blood glucose, which is a value, an ideal blood glucose level specified by their diabetologist, divided by a parameter CF that we get to tune. So if you think back to Peter Abiel's talk earlier, we had these parameterized policies. This is a parameterized policy, and that's one of the parameters that we can tune, CF. The next term is the size of the meal that the person is about to eat, which we measure in terms of grams of carbohydrates, and we divide that by the second parameter that we get to tune, which is CR. So this is just a parameterized policy for a sequential decision problem. We have 3 decisions. How much to inject for breakfast, lunch, and dinner. And these are correlated because the amount that you inject at breakfast changes the state of the person at lunch. Okay, so the way this works now is that someone goes to their diabetologist who says, these are values of CR and CF that will likely work for you. And the person goes off, and roughly 3 to 6 months later, they come back to their diabetologist who says, okay, given how well this has worked, looking at the results from the insulin pump and the reports from the person, after 3 to 6 months, they say, here's how I think you should change these parameters CR and CF. And so this raises the question, can this process be automated to some extent? If not to replace doctors, then to handle cases where someone doesn't have the opportunity to go see a doctor every 3 to 6 months. And so there's been some really great work coming out of the University of Alberta, where the Intelligent Diabetes Management Project, which is a collaboration between the University of Alberta and the Alberta Diabetes Institute, they show that this problem can be treated as a reinforcement learning problem. And there's a master's thesis by Mason Bastani working with Russ Greiner. So how is this modeled? Well, the state is the state of the person. The observation at one step is the current blood sugar levels and the size of the meal they're about to eat. The action is how much insulin the person should inject. And this repeats 3 times for breakfast, lunch, and dinner, and we can treat that as an episode. Okay, so this is a reinforcement learning problem. So I've listed out several problems where safety is kind of a concern. And to really hammer home the problem right now with non-safe reinforcement learning methods, I want to ask a question, which is this. If you deploy an existing reinforcement learning algorithm, pick your favorite one, fitted Q iteration, to one of these problems, do you have confidence that the policy that it produces will be better than the current policy? Do you trust that the new parameters that you pick for this diabetes controller are actually going to be better than the current ones? Do you trust that your method for serving up ads that's proposed by your favorite RL algorithm will be better than the current existing method? So put differently, can I get hands for if you've ever implemented an RL algorithm on any problem where you didn't just run it, you actually kind of chose the step sizes, you chose the representation, and it can even be mountain car. Hands? So quite a few of you. Most of you have implemented something. Keep them up, keep them up, keep them up. Okay, so leave them up now if the first time that you hit run, it worked. And put them down if your first choice of step sizes and representations wasn't right. So this is the problem, right? The first time that you run an RL algorithm, it typically doesn't work right. You need to do a lot of adjusting and tuning before it works. And this is the difference between a lot of these proposed applications and a lot of the successes that reinforcement learning has had so far. The successes are for applications where it's okay to tune our representation, to tune our step sizes, to tune our hyperparameters. Take Atari, for example. Google did a grid search over the step size parameter for this. So it's completely okay to do this. It's okay somewhere on a Google server to have Atari agents that are just losing millions of games of Atari over and over and over again while they do this search. And then at some point, they find step sizes that work, and they can report that result, and it's a cool result. That is not okay for a medical application. We can't tell someone, sorry, this treatment didn't work for you. Maybe for the next person, we'll get our step sizes right? We can't do this. We need methods that on the first shot, you hit the button and you know that it's going to work. Or at least you know that it's not going to make matters worse. Okay, but that's not to say that, oh, these methods are bad and we should only use these methods. Not at all. These are different sides of reinforcement learning. There can be applications where risk isn't the main concern. And also there's another point, which is a lot of us got into this because we're interested in intelligence. We want to understand what is intelligence, where does it come from, maybe how do we work, can we create a machine that's generally intelligent? And that work tends to fall over in this category. So in the rest of this talk, we're going to talk about things that personally I don't think really describe much about what is intelligence or get at that problem. It's more about taking what we've learned in reinforcement learning and saying, can we apply this responsibly to some real problems now? Okay. One other point that I want to make is that learning curves are really very deceptive. And so I picked plots from one of my own papers so I can bash it. These are from a 2013 NIPS paper with Will Dabney that we called Natural Temporal Difference Learning. So here's our method. Our method is this green one. And many of you have probably seen mountain car and cart pole. Mountain car, you're trying to get to the top of that valley. Cart pole, you're trying to keep the pole balanced. So our method on mountain car gets a near optimal policy after a single episode. So it dilly-dallies around this mountain a little bit, learning. It gets to the goal, and after that, it's almost optimally getting to the solution every single time. Same for cart pole. The pole falls over a single time. And after that, it never happens again. It always keeps the pole balanced. So this seems like an outstanding algorithm, right? But this is deceptive. So the thing is, this is really after billions of episodes of tuning. So first, we did millions of episodes of setting all of the different hyperparameters. And this is standard. When you read an RL paper, it says we manually tune the hyperparameters or we did a grid search. So millions of episodes that went into the parameters optimization. There's also probably another millions that were human intuition from working with these domains in the past. So we've worked with mountain car. We know that the Fourier basis with linear function approximation works really well as a representation here. And that came from many past trials. And also there's billions of episodes that went into experimental design. People making sure that this task is possible. We're not asking something that's completely impossible, and our reward function isn't poorly designed. So going into these plots is a lot of learning ahead of time and adjusting of the system. And so we should be careful when we look at these to say, well, if I apply this to diabetes treatment, I really need to worry about these. I can't just look at this horizontal axis there. Okay.
Question.
Yeah.
So here, are you saying that basically here you just overfitted your parameters to this task?
Yes, essentially. We've found the perfect step sizes, the perfect exploration rate, so that for this task it works. Yes. I don't believe that our algorithm is so amazing that it never dropping the pole here. This is a fluke of the order of the Fourier basis, which sets the exact parameters of the representation, with that step size, with that exploration rate, just happens to work out perfectly to solve this problem. So yes, we've overfit the problem.
I mean, that builds on a few comments that we've seen throughout the week, but even the notion of overfitting in RL is not as clearly defined as in supervised learning. And so I think that's one of the challenges.
Yeah. Anyway, so I think I've finished the definition of I haven't finished the definition. I've talked about background of notation and why we should care about safety and what it is that we want. So let's define safety. So what do we want? We want an algorithm that, as I said, when we hit the go button, it works on the first try. So it has to be guaranteed to work, or more specifically, for the rest of the talk, other than when I talk about other definitions of safety in a moment, when I say a safe reinforcement learning algorithm, I mean one that can give this guarantee. One that can say, with probability at least 1 minus delta, I'm not going to change your policy to one that is worse than the current policy. I'm not going to make things worse. So delta here is the probability that I'm going to do something bad. And a key property of this is you, the user, should get to choose this parameter delta. You can choose the probability that I'm allowed to fail or do something bad. So what my algorithm should do is sit there and collect data. If you choose a very low probability of failure, I might have to sit there for a long time collecting data before I can say, OK, here's a policy that's better. And this guarantee should not be contingent in any way on any hyperparameter settings. So this guarantee just has to actually hold. So put in pictorial form, we want to create this black box, which takes as input some historical data D. This is the data from running our current policy for serving up advertisements, our current policy for treating diabetes, and a probability 1 minus delta, and produces a new policy pi that satisfies this. The performance of this new policy is at least the performance of the behavior policy with probability 1 minus delta. So with high probability, our new policy is at least as good as the current one. Our black box is also allowed to say no solution found. If you say, here's data from 3 users, give me a better policy for serving up advertisements with 99% probability, we can't do it. We have to say, given 3 users, I can't satisfy this guarantee that you've asked for. So we have to be able to say, I can't give the guarantee that you want, which is no solution found. And that really means just return the behavior policy. Keep running the policy that you've been doing, because I can't improve it with high probability yet. OK, so what are some limitations of this setting, just to make them explicit? We've assumed that an initial policy is available. We're not saying we're going to learn from scratch to solve some new challenging problem. We're assuming that we have some policy for treating diabetes, some policy for serving up ads, and we're just going to try to improve it. We're also typically going to assume that this policy is known. So there's been some recent works in progress toward replacing and getting rid of this assumption. But for now, we're going to assume that we know the current policy for serving up advertisements. And we're also going to assume that the currently deployed policy is stochastic. So there's some randomness in it. And we're also, for now, going to look at the batch setting. So this isn't online learning where we see one state, we change our policy, we see another state, we change our policy. This is, I gather a bunch of data and I make a change to my policy. OK, so just to, again, drive this home a little bit more, what are we looking for? If this is episodes, and this is the performance of the policy, so a standard learning curve, the first time that you run a typical RL algorithm on this, it'll do something like this. It'll completely diverge. You'll tweak your learning parameters. And it'll do something like this. It'll start to work. You'll get the step size in the right range, the value functions converging. And eventually, you get the right parameters, and it does really well. What do we want this process to look like when you're using a safe algorithm? Well, actually, first, it's worth mentioning that there's a trivial safe algorithm. Has anyone seen it and thought, wait a minute, there's something wrong here? What is an obviously safe algorithm, according to this definition of safety that ensures this? I think you all just said it at once, which is do nothing. Right? Always return no solution found. Return the behavior policy. And that is safe. So that does this. It says just always return the current policy. We're not doing something bad, and it satisfies our definition of safe. It's not a particularly interesting algorithm, though. So hopefully our algorithm will sometimes actually change the policy and improve performance. But we want the guarantee that we're not going to make it worse. We're not going to go below that initial policy's performance with high probability. And eventually, what we'd really like to see, and what we'll see at the end, are some plots that look like this. We're getting improved performance, and typically it's going to lag behind. We're not going to be as fast as that unsafe method that has been overfit to the problem, that has been perfectly tuned for this problem. Because we're guaranteeing that on the first run, it's never going to produce this behavior. OK, so I pitched my definition of safe and what I think safety should mean. But I should mention, there are many other definitions of safety. And safety is a broad topic in reinforcement learning. So for example, there's a survey on reinforcement learning that has nothing to do with what I've talked about for safety so far. So in that paper, they have this as table 1. This isn't actually their table. I just recreated it. Where they break SafeRL into a few different categories. And I want to spend a little bit of time talking about this one, because it's worth knowing about. So they break SafeRL into these categories. The first one is changing your optimization criterion. So this argument is that for some problems, expected return, mean sum of rewards, doesn't capture what it is that we want to optimize. And so we should choose some other objective that better captures some notion of risk. And the other one, and I'm going to talk about a couple of these on the next slide. The other one is making changes to the exploration process. And most of the methods that they list here are things like inverse reinforcement learning methods and learning from demonstration. So can I bias my initial learning by learning from a human in order to not have that initial learning period where I'm basically flailing randomly? And I would argue that what I'm going to describe in this talk is a third category here, which is changing the learning process. But let's talk a little bit about changing the objective function, because again, it's a common topic in reinforcement learning. So what we optimize right now is expected return, so expected sum of rewards. So let's say that this horizontal axis is the performance axis. So this is higher returns, lower returns. And this is the distribution of returns produced by some policy pi, or we'll call it the blue policy. And that's its mean right there. So this is some policy. Let's say that I give you a different policy, the red policy, that produces this distribution over outcomes. So it has much higher variance, and its expected value is a little bit higher. Which of these two policies is better? So first, if I'm a casino, well, I'm not like the building. If I'm running a casino, then which of these is better? So these are the returns from some slot machine of some sort. Which one is better for me? Which one? I heard someone say the red, and I thought I heard someone say the green. Could I get a hand? Anyone? Which one's better? And why? Yes, the red one, because the expected value is higher. I'll make more money in expectation, and if I lose money sometimes, that's okay, right? So expected return is a decent notion of optimality here, maximizing expected return. But what if I'm a doctor? What if these correspond to patient outcomes, and somewhere over here is something like the patient dies? In this case, which of these two policies is better? The blue, right? Because yes, it has slightly lower expected performance, but we don't have this really high risk down here. So maybe I need a different objective function other than expected sum of rewards to capture what it is that I want to optimize. So let's do this. Let's come up with some other objectives that capture this. One idea is to penalize variance directly, which is what we saw on that previous slide. So we can say that our objective function now is the expected return, just as before, minus this term, where lambda here is just a scaling parameter that says how much we care about variance, times the variance of the observed returns. And if we make lambda large enough in this, then the blue policy, or the red policy, will be better than the blue. It will say, try to get a policy that performs as well as possible and has low variance in the results that it produces. And there's some good work from Scott Kindersma on this and doing policy gradient on this objective. There's another popular one, which is value at risk and conditional value at risk. CVAR is also called, I think, expected shortfall. So what do these do? Let's say that this is the distribution of returns that we see. Instead of returning the mean as our objective, value at risk says take the percentile, take some alpha percentile, where here alpha would be 5%. So what is the return such that 95% of the returns that we get will be bigger than that value? And that is the VAR. So it's the sum of rewards where we know 95% of the time I'll get at least this much. That value is what you would optimize in that case. And then CVAR takes the mean of this probability mass that is lower. So these are all notions of trying to optimize the worst case in some sense. Okay, so for some applications, like we said, for medical applications, maybe this is the right objective. It's the one that we should care about. But this just changing our objective function doesn't address the motivation that we had before. We still have to produce an algorithm that optimizes these objective functions. And the resulting algorithms are often very similar. And we need them to work on the first shot. So I view this as kind of orthogonal to what I'll be talking about in the rest of the talk. There's a choice of objective, and then there's ensuring that we actually increase that objective when we run it. Was there a question? But I'm happy to talk about this more afterwards. OK, so there are, what was I on? I was on, right, so it's kind of an orthogonal question. There are other definitions of safety. For example, there's a paper by Remy Munoz and others where they say that an algorithm is not safe if it doesn't handle arbitrary off-policiness, where where handle means give asymptotic convergence results. So like Sarsa lambda has asymptotic convergence results in the tabular on policy setting. So this is a completely different notion of safety. And there are others. So Akmetalu, working in Claire Tomlin's lab at Berkeley, they've done some work that's kind of related to adaptive control. And this is something that people often think about first when you think about safe RL, and that is state avoidance. So maybe there's some region of state space that I want to ensure that I never reach, that my agent never enters these dangerous states. They were working with quadcopters. It never crashes into the wall. And these methods typically rely on having some strong prior knowledge about the environment, distribution over possible worlds that you can be in. And this is, again, very closely related to adaptive control. Then there's PackRL, which for the sake of time, I'm going to skip over this, but it is also related. OK, so we've now defined our notion of safety for the rest of the talk, which is an algorithm that when I hit the go button, it's guaranteed to work, or at least not make things worse with high probability. How do we make this? Well, there are going to be 3 components that we need to build in order to do this. And the first one is off-policy policy evaluation, which is really awkward because that middle policy. I'll talk about why it's there. And then high confidence, and then actually creating the algorithm. So let's go through what these are, and then we'll delve into each one in detail. And we're actually going to spend the most time in this talk on this first one, which is a paper by Doina Prekup from the year 2000 on importance sampling. OK, so what is off-policy policy evaluation? We're going to try to make this black box in the middle of the screen. And it takes 2 things as input. The first thing is historical data D. So we've run some current policy, and it's produced outcomes. So remember, D, the historical data, is a set of histories, a set of episodes. So for digital marketing, this is the data from all of our users. And the ith episode is the data from the ith user. OK, so we have our historical data produced by that behavior policy, our currently run policy. And we also are given some newly proposed policy, which we're going to call PI-E. And E is for evaluation, because we're going to evaluate this policy. OK, so given the data and this policy, so imagine that I just have collected data and someone else ran an RL algorithm and said, this policy is great, you should run it. And what we'd like to produce as output is a prediction of the performance of this policy that the other person proposed. We'd like to predict how good would this policy be. And the catch is, this black box is not allowed to run the evaluation policy. Because you can imagine where we're going to use this. We're going to use this to ask, is it safe to run this new policy? And it could potentially be a dangerous policy, so we cannot actually run it. So we need to use the data from our current policy to evaluate this new policy, not running the new policy. This is off-policy policy evaluation. Why the extra policy? So there's also off-policy evaluation, which typically refers to trying to estimate a value function using data that came from running a different policy. And here we're not estimating value functions. We're predicting the performance of a policy, predicting expected returns of an entire policy. So that's the second policy. OK, what is the second problem that we're going to solve? We're going to make a second black box that takes the same historical data as input. It takes that same policy that someone else has proposed. But we're not satisfied with just an estimate of how good that policy is. We're going to try to bound it. So we're also going to take a probability 1 minus delta as input. And we're going to produce as output a 1 minus delta confidence lower bound on the performance of this new policy. So we're going to say that policy that you gave me, with probability at least 1 minus delta, it's going to be this good. So we're lower bounding its performance. You can see where this is going to be useful. To be safe, we can't just predict, yes, I think this policy will be better. We need to say, I think this policy will be better, and I guarantee it's going to be at least this good with high probability. And then we'll compare that to our current policy to see if we can return that, the new policy. And again, just as before, we have to do this without deploying the evaluation policy. OK, so then the last step is to take this and put it together. So we're going to make a third black box that takes the historical data as input, no policy. It just takes the data and a probability 1 minus delta, and it produces that new policy that comes with our safety guarantee. So that's kind of putting the pieces together. OK, so let's delve into these 3 problems. The first one being off-policy policy evaluation. And here the talk, I'm going to get very specific so that hopefully coming out of this, you will be able to implement that first one, methods for the first one or the second one, though there's a lot of hand waving that goes into the third one. So we're going to kind of delve into the math of it. OK, so let's talk about importance sampling. Importance sampling is what we're going to use to solve this off-policy policy evaluation problem. Just so you have an idea, can I get hands for if you've seen importance sampling for reinforcement learning? OK, great. So a little less than half. So let's delve into what is importance sampling and how does it work. So this is just a review of our notation. H is a history or a trajectory, and J of pi is our objective. So what we're going to try to predict is the performance of that evaluation policy. OK, so this picture depicts all of the possible histories that could ever occur. Every possible outcome that could occur when we run our controller for treating diabetes. We'll view policies then as a distribution over these outcomes, because that's all a policy is. When you run a policy, we get an outcome, and it's not deterministic. So there's some distribution over the outcomes that occurs when I run a policy. If I were to run the evaluation policy, the policy that I'd like to predict, and this is what we're not allowed to do, because this evaluation policy could be dangerous, right? If I were to run this policy, I'd get samples from this red distribution, and it would be really easy to estimate the performance of the policy. I'd use the Monte Carlo estimator. I would just average over my n samples in the data the observed discounted sums of rewards, the observed returns. And this would be my estimate of how good the evaluation policy is, right? How do I do this, though, when my data doesn't come from the red distribution? What do I do when my data comes from the blue distribution, the distribution over outcomes that occurs from running the behavior policy, the current policy, and I wish it came from the red distribution? What do? Well, I'm going to take a weighted sum. And this is what importance sampling does. How does this work? Well, what this weight does is it says take the third trajectory down. This is a trajectory that we're not going to see very often. But if we could run the evaluation policy, we would see that outcome much more often. It has a higher probability under the evaluation policy. So this is an outcome that we would see more, so let's give it a large weight to pretend that we would have seen this more often. What do we do in the opposite case? So this third one from the bottom. This is an outcome that in our blue bag, the bag we actually have, we see this outcome a lot. But if we were to run the policy that we want, the evaluation policy, we wouldn't have seen it as much. So we'll give it a small weight, a weight that's less than 1, to say pretend that I saw this outcome less frequently. And that's all that importance sampling does. It says take a weighted average of the observed rewards. And what I'm going to go into next is how do we compute what is a reasonable weighting scheme that implements this intuition? Okay. Also, at some points, I might say importance weighted return. That just refers to the term that's in the red box, because it's the importance weighted return, the sum of rewards. Okay, are there any questions so far? I've been kind of flying through this stuff. Is that a hand or a head scratch? Head scratch? Okay. Okay, cool. So let's delve into the derivation of where those weights come from. And I think the easiest way to do this is to set it up not in the context of RL, but to do it just using kind of general notation for general estimators, and then we'll apply it to reinforcement learning. So let's do that. Let's let x be a random variable that has some probability mass function p. And in our case, x is going to be a history, an outcome, and it was generated by our evaluation policy. So p in this case would be the distribution over outcomes that results from running the evaluation policy. But for the general case, p is just a probability mass function for this random variable x. Let's let y be another random variable that has a different probability mass function, which is q. And for just in case anyone's blanking on it, probability mass function, that just means that p of x would be the probability of that outcome x. Okay, so let's let y be a different, getting ahead of ourselves. Let's let y be a different random variable that has a probability mass function q, but which has the same range as x. So really you can think of this as p being one distribution and q being a different distribution over the same things. And in our case, the things are episodes, and p is the evaluation policies distribution, and q is the behavior policies distribution, the distribution that results from running our current policy. Okay. Next, we're going to define a function f. And what we'd like to do is eventually we're going to compute the expected value of this function, of f of x. But f is just some function. And in our case, f of x, remember, x is just a history. F of x is the return of that history in our case. And what we'd like to estimate is the expected value of f of x, but we only have samples of the random variable y. So we'd like to estimate the expected return when trajectories come from the evaluation policy, but we only have trajectories that came from the behavior policy. So that's how this is going to map back. But because we're going to use this a lot, I'll write it on the board just so you don't forget. We're trying to estimate the expected value of f of x, where x comes from p, and we have samples y that come from some distribution q. Okay. So how do we do this? Oh, there's one more thing. We're going to define these terms because I'm going to be very precise in our derivation. We're going to define capital P to be the support of P, capital Q to be the support of Q, and capital F to be the support of F. What is support? So the support of any of these, let's use P for example. The support of P is the set of x such that P of x is not 0. Right? So it's just all of the outcomes that have non-zero probability under this distribution P. Yep?
Are all trajectories on the behavior policy possible on the evaluation policy?
We'll come to that. Yeah, we'll come to that. For now, we're not assuming that yet, but we will assume something related to that. Okay. Any questions? Cool. Okay, so I need to go faster. Okay, so what is the importance sampling estimator? This is the importance sampling estimator. I'll just state what it is, and then we'll derive why it's a reasonable scheme. So given our one sample of this random variable y, the importance sampling estimate for the expected value of f of x, so given one history from the behavior policy, our estimate of the performance of the evaluation policy is this. So this is our weight, and that would be the return. So this is the weight. What is this weight? It's the probability of the outcome under the evaluation distribution, or the target distribution, divided by its probability under the distribution that we're actually sampling from. So if this would be more likely under the distribution that we wish we had, p, then this will be larger than 1. And if it's less likely, this will be smaller than 1. So this is exactly the intuition that we talked about. But why is this ratio really what we want? So let's work out what is the expected value of this importance sampling estimator. OK, so the expected value of this importance sampling estimator is, well, let's write it out. So we sum over all the possible events y. And we have q of y, because y comes from the distribution q, times the estimator. It's just the definition of expected value. Why am I doing y in q here? So we have to sum over the support of this function q. But why don't we sum over anything else? We don't sum over anything else because for y's that aren't in q, we'd be dividing by 0. And so this expected value would be undefined. So really, for this expected value, we can only sum over the elements that are in the support of q, that distribution. OK, so what can we do next? We'll just do a change of variable. So y is just a variable name here. Let's just call it x instead. That's all we've done here. OK, what did I do next? What I did next is I canceled this q with that q, because it's on the top and on the bottom. Those go away. And so we get p of x, f of x are the only terms left. But we've split our sum into different components. So I guess a Venn diagram could help here. So we have p and q. And what we wanted to do is sum over q, which is that region right there. So what did we do? We split that into 3 sums. We summed first over p. So we included all of this. Then we summed over not p and q. So that's all of this, not including the parts that are in p and q. And then we subtracted off, the bits that are in p and not q. So what is in p and not q? That's all of this. So we subtracted this back off, and that means we're just summing over q. So we haven't changed anything. We've just rewritten. We've split this sum into 3 different components. Right? OK. So here I'm keeping the first term and keeping the second term, but we removed the middle term. Why did we do this? So for any x that is not in p, so remember capital P is the support of p. It's the values for which p of x is not 0. So if you're not in p, p of x is 0. So these terms are all 0 for every term in this sum. So that middle sum is just 0. So we can get rid of it. OK. So how do we go from here to getting the expected values what we want? We need to make some assumptions. So on this slide, I'll make one set of assumptions. And on the next slide, I'll make a different set of assumptions. So the first set of assumptions that we can make is that p is a subset of q. So what does this mean? The distribution that we wish we could sample from is a subset of the distribution. Sorry, this is a subset of the support of the distribution that we actually have samples from. So in other words, if we'd like to know the expected value under one policy, we need to be able to see everything that that policy could do in the policy that we ran. If the policy that we're running never takes some action in some state, we don't know what that will do, and we can never know what that will do. And so our evaluation policy can't take that other action in that state. We need to be able to see everything under the sampling distribution that could ever happen under the evaluation distribution. So that's what this assumption means. And you can actually relax this a little bit, exercise for you to do at home later. So let's complete the proof with this assumption. And I'll remind me later if I forget what this assumption exactly means in our RL case. It's something that we can check very easily. OK, so let's complete the proof. This is just copying the last line from before. I've removed the second term. Why did I do that? So P is a subset of Q. So that means we have P and Q. So this term is summing over the elements that are in P and in not Q. So they're in P and in not Q. So it has to be both here and out there. That's nothing. So this is summing over the empty set. So this term is now 0, and we get this. That's just the definition of the expected value of f of x. So we're done. So we have that in this case, given this assumption, the importance sampling estimator gives an unbiased estimate of this expected value. So thinking back to our case, the ratio of the probability of the outcomes under the evaluation policy and the currently run policy times the returns is an unbiased estimate of the true performance of this evaluation policy. And I will flush that out in detail in a moment. First, I want to show that we can complete this with a different set of assumptions. So let's instead assume that the function we're trying to estimate, f of x, which in our case is returns, is non-negative. So it only takes positive values. What can we do then? Well, this is just copying what we had from the end of that previous slide. What happens to the second term here? P is positive. Well, I just gave away the answer. P is positive. F is non-negative. So we're subtracting a positive term. So our expected value is going to be less than this value, which is just the expected value. So we don't have an unbiased estimator. We have an estimator that has negative bias. So the expected value of this importance sampling estimator will be less than the true performance of our evaluation policy, which, if you think to what are we about to do with this, is going to be completely OK. So what are we going to do with this? We're going to predict the performance of a policy and then ask, is its performance at least this good? If we're underestimating the performance of this policy, we're just going to be conservative. So, Csaba?
Yeah, I'm wondering, so you drop the assumption here of the support relationship between P and Q. So there could be that this positive probability you're going to sample at y such that Qy is 0.
Sorry, I'm having trouble hearing. There are a lot of squeaking chairs. Yeah.
So is it possible that this positive probability you're going to sample at y such that Qy is 0?
No. We're in the discrete setting for here at least. So we would never sample something with Q of y being 0. That's saying I'd sample an event with 0 probability. And in the continuous case, this would be a density function, and the density wouldn't be 0 for something I'd sample. And in the, yeah, I don't know in the full measure theoretic case if this holds up. So importance sampling works in the measure theoretic case where this ratio is the Radon-Nikodym derivative, and you need absolute continuity. And I don't know if you need absolute continuity anyway. That's a different question. Yep. Sorry, there's some weird noises also. Yeah. Than mass functions, you mean? Yeah, so this definitely works for density functions. And I suspect it works for the full measure theoretic probability case. Certainly if you have this assumption, which really means that I always mix this up. I think it's P is absolutely continuous with respect to Q. If you have that, then this works in the measure theoretic setting once you have the support.
I mean, do we need it to be normalized, or can it be something like an energy model or something like this?
Do we need to be?
Do we need this P and Q to be normalized distribution?
So in the case that I've done and seen, these are always probability distributions. So they're normalized to integrate to 1 or sum to 1. If these were distributions that weren't probability distributions, I'm not sure. Yes, I will get to the ratios. I think I see where this question might be going. So I think I will answer that later. Yep. Yes, I will answer that. OK. So we said this. OK. So let's apply this to reinforcement learning. Let's get out of this x and y and go back to RL. So x was the thing we wish we had. So these are histories produced by the evaluation policy. We have histories produced by the behavior policy. The distribution P then is the distribution over histories under the evaluation policy. Q is the distribution over histories under the behavior policy. And the function that we're evaluating, f of h, or f of x, is the return, the observed sums of rewards. OK, so what is then the target value we're trying to predict? It's the expected value of f of x. So that's the expected return given that our trajectories, x, come from the evaluation policy. It's the performance of the evaluation policy. And we're assuming that either the support of the evaluation policy is a subset of the support of the behavior policy, or that the returns are non-negative. And I'll talk about this more later, I think, if I don't ask at the end. Okay, so what does this mean? Let's plug all of this in and get our importance sampling estimator. It is this. The importance sampling estimator from one history coming from the behavior policy is the probability of that history under the evaluation policy divided by the probability of that history under the behavior policy times the return. So think back to our intuition. We want this weight to be large in the case where this is more likely under the evaluation policy. And that's what this does. If this is more likely under the evaluation policy, this is greater than 1. If it's less likely, this is less than 1. So this is our importance sampling estimator for RL. This is the estimate from a single history, but we have many histories. Our data consists of many different episodes. So if we have many histories, that's our data set D, we just average the importance sampling estimates from each history. Or put differently, it's the average over our n histories of the importance sampling estimates, where this RT is the reward at time t in that ith history. Okay, that question in the back was a very good one. It was, but how do we compute these things? How do we compute this importance weight? We don't know the probability of a history under a policy. So let's look at that some more. So what is the probability of a history under the evaluation policy? That's what we'll put on the top. Well, let's just run through all the terms of that history in sequential order. So it's the probability of the initial state times the probability that we take the first action that we took in that state, the probability that we transition to state S2 and get reward R1, given that we were in that state and took that action, and this is making the Markov assumption, times the probability that we take the second action that we took, times the probability of the second transition, et cetera, right? This is just writing out the probability of a trajectory. The problem is we don't know these transition probabilities. We know our policy, but we don't know these. But when we divide by the probability under a different policy, these terms are going to cancel. We get all these same exact terms except for the action selection parts, the policy terms. So when we cancel all the probability of S1, the probability of the first transitions, we're left with just the pi terms. And we know pi. That's the policy we're thinking of deploying in our current policy. So put differently, that importance ratio is the product over time from initial time until the total horizon of our problem of the ratio of the action probabilities at each time step. Okay. So let's just plug that in. This is what we had before. We plug in that ratio and we get this term in the middle. And this is our importance sampling estimator. So hopefully you could implement this at this point. If I have a data set, this is average my weighted returns, where there should be a little I here in the reward. So this is the action at time t in the ith history. So this is all in the ith history, and this is the return. So if I gave you a data set and a behavior policy and evaluation policy, you can just implement this sum, and that's an unbiased estimate of the performance of this policy. And I got a little bit greedy in making this and thought I would go much, much faster. So at some point we'll skip something, and I think we'll skip this. So we're going to skip we'll go through it really quickly. It'll be fine. So let's do something different. Oh, is there a question? So yes, so if pi e is deterministic, that's completely okay. That means that this could be 1, and this is anything, that's fine. Pi b cannot be deterministic. If pi b is deterministic, then this will actually always be 1. It'll never be 0. But if this is always 1, what ends up happening, we have that support problem. And in the deterministic case, that support problem means, again, we're going to underestimate. And if it's deterministic, it's going to be 0. So what will happen is our estimate will just always be 0 if we run a deterministic policy, and the evaluation policy is different.
We can keep the behavior policy stochastic.
Yeah, so keep the behavior policy stochastic, if possible. And if there's some cases where it's deterministic, try to match that deterministic part in your evaluation policy. Okay, so here's an idea. Instead of using importance sampling to estimate the expected returns, let's use importance sampling to estimate just one reward, the reward at time t. So this is something else that we can do. Instead of estimating the whole thing, just do one piece. What do we get? Well, the importance sampling estimate for the reward at time t is average over our samples, the weighted reward at time t. Where here this weight is the probability not of the full history, but of the history up until time step t. Why is that? It's because the history after time t has no bearing on the reward that we see at time t. It doesn't, so knowing the history afterwards doesn't impact our estimate of this intuitively. And you can show that this remains unbiased. Okay, so this is how we would use importance sampling to estimate one reward. So what we could do is sum over these. We can estimate the sum over time. What am I doing here? Oh, this is the other equation. So this is actually computing this ratio. So we've put the 1 over n sum, the reward, and we're asking what is this ratio? Well, it's just the product of action probabilities to time t instead of to L at the end of the episode. So if we have this estimate of RT under the evaluation policy, we can do per decision importance sampling, which says we're going to just take the weighted sum of these estimates from each time step. So estimate the first reward, add to that our estimate of what the second reward will be, add to that our estimate of what the third reward will be, etc., and we get an estimate of the total return. And that looks like this. So this is just plugging in the sum from t equals 1 to L, gamma to the t, of our estimate using importance sampling for the reward at time t. Okay. I'm going to skip this slide. Actually, I want to point one thing out. So we're going to skip the slide, but just look at this. And what happens in importance sampling if the evaluation policy and behavior policy are very, very different? So what tends to happen here? We get, this is really the probability of histories. So we get histories where the probability under the behavior policy is larger. The probability under the evaluation policy is smaller. So we tend to take actions that are likely under our sampling distribution. So this tends to be larger. That tends to be smaller. And so if we have a long sequence of these, this tends towards 0. So as we get longer and longer episodes, or as these two policies become more and more different, the importance weights tend towards 0. And so this means that when these policies are sufficiently different, or when horizons are sufficiently long, it's not here, importance sampling has high variance, and it tends to just always say the estimate is 0, the estimate is 0, the estimate is 0, which is a terrible estimate. So there's the question of, right, so here's the case where importance sampling tends to be 0 when these are different. So what is importance sampling doing? Initially, its estimates tend towards 0, and as we get more and more data, they tend towards the correct value. And this isn't necessarily the behavior that we want. So here's an idea. Ignore that, ignore this. This came from something I didn't talk about. Can we make a new estimator that is going to have much lower variance than importance sampling, but has some bias? So it's no longer going to be unbiased, but it's at least going to be consistent, so it'll converge to the right value. And this is what weighted importance sampling does. So what is weighted importance sampling? Well, WI is our importance weight. The importance sampling estimate was just this, the average of our weighted returns. And you can push the n in there onto the weight term. So I just rewritten importance sampling. What weighted importance sampling does is it says instead of dividing by n, let's divide by the total sum of our importance weights. And here we're back to ordinary importance sampling, not per decision for now. So what does this do? So you can view this whole term as a new weight. And what we've done is we've normalized these weights so that all of them sum to 1. So you can view this as a weighted average of the observed returns. And this has some really nice properties. So first, what is weighted importance sampling equal to if we have only a single history? And I will take a break from talking to let you think about this. Does anyone have an answer? What was that? It equals the original policy. So it equals, I mean, it's not a policy, it's a number. It's the, you're getting at it. Yeah, it's the return from the behavior policy. So what happens is we only have one weight. We divide by that weight. So these are just 1. And so what we get out is it's the observed return under our behavior policy. This is the Monte Carlo estimator of the performance of the behavior policy. We'd like to evaluate the evaluation policy. This is estimating the performance of the behavior policy. What happens, though, as n increases? So there's this nice property which I won't run through, but it's straightforward to show that the expected value of these importance weights is always 1. So that means that this sum in the limit is converging to n. And so in the limit as we get infinite data, that sum of importance weights converges to n almost surely. And when this is n, that's importance sampling. That's ordinary importance sampling. So we have as an estimator that begins as a Monte Carlo estimator of the performance of the behavior policy. And then as we get more and more data, it acts more and more like importance sampling. So it's correct asymptotically, but it ends up having much, much lower variance. And that is all I will say for weighted importance sampling. So we've gone through 3 forms of importance sampling: importance sampling, weighted importance sampling, and per decision importance sampling. There are many other types. You can also do weighted per decision, which is sometimes called consistent weighted per decision. Also, you can do special forms of importance sampling when those supports aren't equal. You can ignore importance sampling and just build a model of your MDP and compute the performance of your evaluation policy on that model of an MDP. You can try to combine these model-based estimators with importance sampling, and that's what these two, doubly robust and weighted doubly robust, do. You can also recognize that the environment might not be stationary, and so there's some time series prediction in this, and combine importance sampling with time series prediction, and there's one last one that does more combination of the model with importance sampling. And there'll be references for all of these at the end. So just to point out, there's many more techniques for off-policy evaluation. Okay, so what do these results typically look like? This is a typical plot for, this is actually a toy domain, but it's representative, that shows the amount of historical data that we have and the mean squared error of our different estimators. And this really is what we tend to see. These are log axes, so these are order of magnitude differences in error of these estimators. So up here is importance sampling. Per decision importance sampling tends to do a little bit better. It's lower variance. And if we jump to weighted importance sampling, that's the yellow line there. Weighted importance sampling does roughly an order of magnitude, in this case, better than ordinary importance sampling. But that's a trade-off. It's no longer unbiased. So we're getting some bias, but that bias estimator is much more accurate. And then weighted per decision does a little bit better still. Next up is the doubly robust estimator. That's combining with a model. That's blue. And I think weighted doubly robust is kind of the, if you want just the most accurate estimate, it's one of the state of the arts at the moment. And a key thing of this plot is to show, yes, I've described these more sophisticated methods, and it's tempting to say, oh, well, I'll just implement importance sampling first. This is 3 orders of magnitude approximately difference in performance. So it is important to use these more sophisticated techniques if you're actually trying to do policy evaluation. Okay, so let's go on to the next step, which is how do we do high confidence off policy evaluation? So we're creating this new black box that doesn't just predict the performance of the policy, it lower bounds the performance. So it says that new policy will be at least this good. That was the wrong button. Okay. So the way that we're going to do this is we're going to use our importance sampling estimates, and we're going to put them through some method that takes our n importance sampling estimates and spits out a confidence bound on their mean. And one way of doing this is using Hufting's inequality. So let's review Hufting's inequality quickly. Let x1 to xn be n independent and identically distributed random variables that are between 0 and b. So the example I like to use for this is, let's say that we're going to measure, let's pick n is 30. We're going to pick 30 people from the surface of the Earth with replacement so that it's identically distributed. And I'm going to measure their heights. So I measure the heights of 30 different people. We need these to be bounded between 0 and b. So you can't have a negative height, so we're bounded by 0. We need an upper bound of b. So the easy way to do this is you just define if someone is taller than 3 meters, we're just not defining them as human. So it's 0 to 3 meters. Okay, that should not have shown up yet. Pretend this isn't here yet. So what Hufting says is with probability at least 1 minus delta, this inequality holds. So the true expected value of our random variable, the true mean height of humans, is at least the sample mean minus this term. So it's the sample mean that we observed minus b, that's the range of the random variable, times root log 1 over delta, that comes from the probability that we want, over 2n, where n is the number of histories, the number of trajectories that we have. So we know all of these terms. We could implement this, for example. And also notice that this matches intuition. So the true mean height of humans is at least our sample mean minus some term. And this term says how far down you have to go given the number of samples that you have. And a nice property of this is we're not making any other assumptions. Nowhere in here are we saying these xi are normally distributed or anything of that sort. Regardless of their distribution, this will hold. So how do we use this for importance sampling? Well, it's given away, or for reinforcement learning, it's given away by the part that came too soon. We're just going to plug our importance sampling estimators in here. The importance sampling estimator is an unbiased estimate of the true performance of this evaluation policy. So the expected return of the evaluation policy is at least our importance sampling estimator minus this. So this gives us a lower bound. Unfortunately, this doesn't work very well. So if we actually plug this in for mountain car, where we normalize returns so that they're always within 0, 1, and we pick an evaluation policy whose performance is 0.19, so it's not a very good policy. We can then pick 100,000 trajectories of data, of historical data. Remember, on that other slide, we solved this in something like 2 trajectories. So we're going to take a ton of data, and we're going to then lower bound the performance of this evaluation policy using these 100,000 trajectories from, I think, the uniform random policy. So what are we doing? We're taking those 100,000 trajectories, computing the importance weighted returns. Then we're taking those and subtracting off from the importance weighted returns this term b root log 1 over delta over 2n. And we get negative 5.8 million, which is useless because we normalized returns to be between 0 and 1. This is just not at all a useful lower bound. So what went wrong? What went wrong, ignore this because I skipped over it. What went wrong is this range term b. B is the range of our random variable, and the importance sampling estimator can have a huge range. The range scales exponentially with the horizon of the problem. So how can we fix this? Well, we can just not use Hufting's inequality. There are more sophisticated concentration inequalities that we can use. This is one of them, and this is actually the one that I would recommend. It comes from this AAAI paper, which looks really scary, but it's all terms that we can know. It's just a matter of plugging in values and letting it chug along. And if you use, so remember the actual performance of this policy is 0.19. Hufting was negative 5.8 million. You might say use an empirical Bernstein bound if you're familiar with those. That also doesn't work. There's an obscure one called Anderson and Massart's inequality, which actually works reasonably well. But you can get much better using this cut inequality. So just use a different inequality, but the intuition is the same. There's another thing that we could do, which is forget using these exact concentration bounds and make some false assumptions. So, which I say too lightly. So this is student's t-test. It says if the sum of our n random variables is normally distributed, then this inequality holds. The true mean is at least our sample mean minus this other term, where this is the standard deviation, and that's the t statistic. And this tends to be much, much tighter than Hufting's inequality. But it's relying on the assumption that the mean of our random variables is normally distributed. Thankfully, the central limit theorem, yes, tells us that the sum of any number of IID random variables tends to be normally distributed as n increases. So this isn't a terrible assumption to make. It's often largely true. And there's another nice result, which is that if the rewards are not negative, then the t-test tends to be conservative. And this has to do with how the t-test works when I have different skews on my random variable. So I'm going to skip over Bootstrap. It's just another competing way. This tends to mean that if I ask for some probability of failure, and I look at the number of samples that I have, and I ask, how often is this concentration bound failing? If I use Hufting's or any of the other concentration bounds, they pretty much never have error rates that match delta. And that's because they're overly conservative. They allow for any distribution of data. Whereas when I use student's t-test for these important sampling estimates, it tends to still be conservative. Whereas Bootstrap methods give tighter bounds, but sometimes have higher error rates than we want. And these are just results saying that, yes, for Mountain Car, we can actually do this. We can lower bound the performance of this policy. And the big takeaway is these are most of the methods that we talked about. This is using weighted and per decision with the Bootstrap confidence bounds. A key thing is this is 0 to 1, and this is 0 to negative 5 to the 45th. This is Hufting with importance sampling. So it just reiterates, you can't just use Hufting's inequality and importance sampling and get this to work. You have to use some of these more sophisticated methods. We also did this on actual digital marketing data and argued that some new policy for digital marketing would be better than existing policies. And I'm going to skip over this quickly. It essentially just says what I've said. Here, if you want it later, is pseudocode, which I have not verified beyond now. So if you find a mistake, email me and I will correct it. But I think it's right. This is pseudocode for doing weighted per decision importance sampling with student's t-test. So you can go through this and implement it, and it will give you a lower bound that holds with probability 1 minus delta on the performance of this evaluation policy, approximately. OK, so let's talk about the last thing, which is safe policy improvement. We wanted to make that box that took the historical data, the probability, and produces a new policy that gives our safety guarantee. How do we do this using the components that we've put together so far? Well, we do it like this. So we take our historical data and we split it into 2 sets. The first set is we're going to call the training set, and the second is the testing set. And this is completely arbitrary, but for now we tend to split it into 20% data in the training set and 80% in the testing set. We then take the testing set and we pick one single policy, pi c, that we think is going to be a really good policy. So you could, in your head, imagine that we're running fitted Q iteration on this batch of data and saying, here's the policy that we predict is going to be best. So we pick a policy that we think is good from this training set, just the batch RL problem. We then take that policy and use the other 80% of our data to run a safety test. What is the safety test? Well, it's our black box from the previous section. We just compute a lower bound on the, we compute a lower bound on this policy's performance using our 80% of the data. So we take that 80%, we use importance sampling to predict this policy's performance. And if we were using Hufting, we then subtract off that term from Hufting. If we're using t-test, we subtract off the standard deviation of the importance sampling estimates divided by root n times the t-statistic, and that's all that we do. So we use one of these high confidence off policy evaluation methods. So once we have a lower bound on this policy's performance, we check, is that lower bound at least the performance of our current policy? If it is, then we deploy the new policy. If it's not, then we don't deploy the new policy. We say no solution found. We say my lower bound was too low, I'm not getting the guarantee I want, so say stick with the current policy. Okay, there's a catch, and the catch is shown by this figure. So let this blue box be the space of all possible policies. And let's talk about how we choose the candidate policy. So if this is our current policy, and this is the policy that maybe we predict is the best policy from our training data, then maybe actually this policy is better. So maybe this gradient shows that policies out in this direction perform better than policies out in this direction. So performance gets better as we go this way. However, the tightness of our lower bounds goes the other way. So remember, importance sampling, we get higher and higher variance as the policies become more and more different, because those ratios get bigger and bigger. Importance sampling tends to give that output of 0. So our bounds get looser and looser as we get farther and farther away from this current policy, not just in this direction. Anytime we get farther away from our current policy, our bounds tend to get looser. So this policy might be one that's much, much better, but the lower bound that we get on its performance can be really, really low. And so we could say, we think this is great, but we can't guarantee anything, and our algorithm would return no solution found. So the optimal policy, the optimal candidate policy to return, is somewhere in between. It's one that balances this trade-off. It's one that we predict back here. The optimal candidate policy is one that we predict is going to pass this safety test. And subject to that, it's the one that we think is going to perform the best. So it's the one where we don't go so far that we're unable to get a tight bound on its performance, and so we say it's unsafe, but we go as far as we can to get as much improvement in performance. And that's just high-level intuition. What this ends up meaning is we need some sort of regularization to keep us close to our current policy. Okay, so in the last 5 minutes, let's just go through a couple of results to say, yes, this really works. It's not just math theory to say, hey, apply these bounds. Okay, so these are results from Mountain Car modified to have a shorter horizon. So whenever you take an action, the agent keeps taking that action for 20 time steps. We're running the random policy. Oh, first we normalized returns so that returns fall between 0 and 1. So the optimal policy has an expected return of 1. Where this black bar is actually the performance of the random policy in this case. What we're doing is asking our safe policy improvement algorithm to produce a new policy that with 95% probability is better. And actually in all of the results I'll show, we're going to use 95% probability. And we're using different variants of the algorithms and different amounts of historical data. So using just 50 trajectories, these black bars correspond to using that cut inequality, an exact concentration bound, whereas these dashed bars correspond to using an approximate one. So they're actually using a bootstrap method called BCA, but intuitively you can think of this as being very similar to using students' t-test to do that bounding. So using that approximate concentration bound, we're actually able to get policies returned sometimes with just 50 trajectories. Using just 50 trajectories, we're sometimes getting, here's a policy that is better. And this will not be wrong more than 5% of the time, approximately, when we're doing the dashed bars because of students' t-test. As we go up, the approximate methods are solving Mountain Car in 200 to 900 episodes, whereas the exact methods take more. But with 5,000 trajectories, we're just instantly jumping to an optimal policy. So this isn't the same as a perfectly tuned natural electrocritic, for example. But we're not taking centuries worth of data in order to do this. We can also do this incrementally. So we can run this repeatedly. We can gather 50 trajectories, run our algorithm. Gather another 50 trajectories, run our algorithm. And then we get these learning curves. And so this is Mountain Car using the student's t-test-like method, the bootstrap method, and this is using our exact methods. So we're solving it in just hundreds of episodes, which when we look at it now and we think, oh, well, we can solve this really quickly with an unsafe method, this seems like, oh, that's only okay. But to put some context on this, when we started trying to do this, back in 2014 if we tried to do this, this would take us millions and millions of episodes. So by all of these advances in policy evaluation, we're able to get this to kind of a tractable amount of data. We can also do some other cool things. So instead of saying, I want your performance to be at least the performance of the current policy, there's nothing stopping us from saying, you need to be significantly better or I'm not going to change anything. So this is mountain car, where the red correspond to different runs of our algorithm. And we're saying guarantee that you're at least, so this is the performance of the current policy, guarantee that you're at least the performance of this blue bar before you change the policy. So I need some significant improvement before you change anything. And our algorithm waits until it has enough data to change the policy so that it's better than the blue bar. And it's still being conservative when it does that. This, to give some context, is the performance of just a well-tuned natural electrocritic. So we're not lagging too far behind it. Okay. We also applied this to some simulated digital marketing experiments. So just to summarize these results, they say that using 100,000 users' data, we are often able to say, here's a policy, it is better than what you're currently doing for serving up advertisements. So we're right in the ballpark of where we want to be. This is, again, results from a different internal simulator at Adobe Research. This was a simple toy problem that we mocked up, just to illustrate, again, the safety property. And this is a very simple mock-up of a digital marketing problem, which the main difference between why this takes hundreds of thousands of users' data is that almost no one clicks on advertisements. So our reward signal is very sparse. And in this mock-up, we just pretended that people actually liked ads and they click on them. So we get higher click rates. So this curve here is a natural electrocritic with optimized hyperparameters. And if we just take the step size, and I think it was 0.01 or something, and we change it to 0.02, it learns faster and then it completely diverges. And this is the problem. We have these hyperparameters that when we set them wrong, it doesn't work. This is the very first time we ever ran our algorithm on this problem. It's guaranteed that it's not going to produce worse performance. It's not going to diverge down to worse policies. So we are slower, but we're giving that safety guarantee. And I'd like to wrap up with that illustrative example that I started with, which is diabetes treatment. So this was the problem of, can we decide how much insulin to inject in order to keep someone's blood sugar near optimal levels? The study by Mason Bastani at the University of Alberta, showing that this is an RL problem, used a simulator called T1DMS. And this is a simulator of this entire metabolic process. And in the US, if you want to do studies on one of these controllers on humans, you have to first do studies on rats, or you can use the simulator. So it's not just an arbitrary simulator we hacked together, it is a high-quality simulator. So we tried to reproduce the results, but using one of these safe algorithms. And this shows the amount of data we're using for a simulated subject, the amount of days of data that we took, and the probability that we're able to change the person's treatment policy to be something different. So how often were we able to say, here's something that's different from the current policy, while ensuring that with 95% probability, we don't make matters worse. And there's another catch. We did something else a little bit different here. We really care mainly about hypoglycemia, low blood sugar. So our probabilistic guarantee is with respect to low blood sugar. So we said try to keep blood sugar near optimal levels while ensuring that we don't increase the amount of low blood sugar that we get. So where is this? Well, we wanted 3 to 6 months. That's 90 to 180 days. Right within that window is where we're able to return policies that are better. So we're using the amount of data that we want. What is this plot? This plot shows what is the probability that we actually did something bad. Right, so we asked for a 5% probability that we increase the prevalence of hypoglycemia. So given different amounts of data, how likely were we to produce a policy that's worse? We're the blue line here. Not once across any of our trials did this increase the prevalence of hypoglycemia. And that's because we're still using concentration bounds that tend to be overly conservative. What is the red line? This is what you get if you use a well-tuned standard RL method. And it kind of explains what's going on. First, it always returns a policy. And what happens is early on, we're getting some data set, and it's random. There's a lot of randomness in when meals are eaten, errors in how big the meal actually was. And because of this randomness in the data set, we can draw false conclusions. Randomness in the data set can make us think that something is better when it's really just a fluke of the data. And so that's what's happening here. We're choosing policies to return that we think are better, but really it was a fluke of the data that made us think this. And what our algorithms are doing is they're looking both at the policy that we're proposing and the data we use to create it and asking, can we conclude that this isn't a fluke of the data, that this policy really is better? And if it is, then we start returning it. So you'll notice right when these policies tend to typically be actually better policies, we start frequently returning policies. Yeah?
How do you solve a cold start problem when you don't have the source data?
We don't. So that was one of the limitations of the setting at the start, is we assume that we have an initial policy that we're willing to deploy. If we have to do cold starts and we're trying to ensure this sort of safety, you need something else. You need something like a prior distribution over models, and that's when you get to kind of the adaptive control style approaches. But this does not solve cold start. So to wrap up in my last -1 minute, just to conclude, there are many different definitions of safety. We talked about one, ensuring that policies are better with high probability. We went through the 3 steps to creating a safe algorithm: predicting the performance of a policy without deploying it, bounding the performance of a policy without deploying it, and then putting those pieces together to actually do policy improvement. And then we talked about some empirical results to say, this is actually possible. We can do this using realistic amounts of data. And some future directions, which you can look at later offline. There are many open questions still to make this better. And that's kind of shown by the list of references. A lot of these are 2017, 2016 references. This is something that's kind of happening now-ish. So there are a ton of open questions left to be answered. And if you'd like to know more about this, the first place to start really is Doina-Prekup's paper from 2000, which goes into importance sampling. Though the weighted per decision estimator has a typo, so something to be wary of. And that's it. Thanks.